In every spaceflight mission, problems are inevitable for the astronauts, from both a mental and physical standpoint. Their bodies are subject to extreme conditions and intense environments, and the regulatory procedures put in place to combat the health issues that arise are sometimes inefficient and time-consuming. One of the main psychological issues that we identified within the aerospace and aviation industry was the issue of orthostatic hypotension, caused by the zero-gravity environment of space. Orthostatic hypotension is a loss of diastolic and systolic pressure on your blood vessels, resulting in lowered blood pressure overall. Astronauts experience this phenomenon after returning to Earth, and as a result of it, they can experience numerous harmful side effects, such as heart disease, organ failure, and even strokes. These issues are harmful to the aerospace industry and to the people who put their lives on the line for the sake of scientific innovation in space.
According to the American College of Cardiology, as of right now, one of the best ways to work against orthostatic hypotension is through a strict exercise regime. However, implementing this regime daily is difficult and tiring for many astronauts. Because of this inefficiency and difficulty of technique, we decided that it was time to work to develop a solution. We set out to create new, more efficient detection methods and began working with a variety of experimental techniques. We started working with different techniques to help blood flow velocity regulation, eventually deciding to develop a compressive suit that would work to create compression at areas where blood flow irregularities were detected. It was important to choose techniques that would accurately detect blood flow velocity, and we decided to use the techniques of Doppler gate imaging and Korotkov waves. We developed a research thesis stating that spot-specific microcompression, through the utilization of techniques including pulse echo Doppler gate imaging, PE, Korotkov waves, and motor-induced compression, would allow for more efficient detection and a lessened occurrence rate for orthostatic hypotension.
The models show the methods that are utilized in compressing the suit. Each motor pack will have micromotors 2 centimeters in diameter, which are utilized to create a pressure gradient that constricts target areas of the body to counteract the irregular blood flow generated by microgravity. These are grouped into large and small motor packs, with large motor packs being placed at areas of high blood vessel concentration, while small motor packs are being placed at the appendages. Specifically, the motor packs are placed at the anterior posterior delt, lumbus, antebrachium, and quadriceps, as can be seen in the 3D model. The micromotors will rotate, pulling up and releasing the fabric based on the needed constriction, as observed in the 2D model. The motor packs work based on an evaluation of blood pressure, derived using Poiseuille's equation of blood flow. By reworking the equation, the variable for pressure can be isolated and then be used to determine the compression pressure that will be needed, and the motors will then apply. At the locations of the motor packs, 64 to 128 pulse echo signals are sent through the LMT, 70 sensors, and then mapped in a triplex to visualize the areas of low blood pressure.
In our MATLAB software, we utilized pulse echo Doppler imaging to measure the decrease in blood pressure velocity irregularities. Pulse echo wave Doppler imaging is a method in which you use a Doppler gate to fire ultrasonic beams, and these beams are displayed across the user's body, and they will reflect a high-intensity color onto a monitor, detecting the results and indicating abnormally high resistance. Pulse echo Doppler imaging requires only one single electromechanical transducer, making it the optimal scientific method to record velocity, as the sensors we use in our study, the LMT70 sensor, only holds one transducer. The first step in this process is firing 64 to 128 pulse echo signals to obtain information about the distribution of blood flow velocity, using the wave reflection as a measure. The second step is firing a second wave of signals around 6 to 16 to quickly estimate the mean frequency shift of blood flow over a large area, allowing it to be mapped onto a color imager in MATLAB to highlight irregularities in blood flow. The velocity in the direction of the transducer is equal to the cosine of the wave velocity, and the software calculates the time taken to travel by adding the initial distance away from the transducer with the velocity times the change in time it took for the wave to reflect. This information will be applied through the LMT70 sensor and will ultimately highlight or color areas in MATLAB imaging software with an irregular blood flow. This is around above or below 1,450 meters per second. The MATLAB data stream will then be sent back to the motors, implemented to create compression in certain areas. In essence, the scientific principles of waves and pulse echo allow us to apply accurate blood pressure sensing techniques in space through our suit. This allowed us to gain data points for individuals, comparing normal blood pressure velocity to reductions based on the simulations we ran. To gauge our decrease in blood pressure velocity, we compared normal methods of blood velocity reduction, such as working out, using the software to see how well our research compared.
Updating the methods to address orthostatic hypotension is long overdue. With the current outdated methods taking away precious time from astronauts, the AerometrX suit would work to circumvent the time-consuming exercise regime currently in place. By passively redistributing blood, the AerometrX G suit allows astronauts to actively engage in other mission tasks while the suit combats the irregular blood distribution caused by microgravity. Further, the suit allows for increased speed in the detection of abnormalities and an increase in the identified abnormalities that would be normally missed by conventional exams. Our research has also indicated that the suit allows for more accurate blood redistribution due to the targeted detection and compression methods that focus on specific regions of the body at a time. In combination, these facets of improvement will significantly reduce the downtime during missions and improve overall mission safety, allowing astronauts to safely dedicate more time to important research during their limited stay in space.